recording the session again today. Later on, I will post this up to you guys. I'll send you an email probably with a link to the video in case you have to leave early, or if you just want to watch any of it again later on down the line. So over the weekend, I guess this is the weekend, yesterday I graded the last homework assignments. Those were mostly very good. So you should have that back by now. And in addition to that, the solutions are posted. Pretty much solutions to everything are totally posted now. So I feel pretty good that the website is set up with everything you guys need to be looking at. So the only thing missing is this review, and I'll be posting it up. Don't forget that after the review tonight, I'm going to have office hours. And then I got more office hours tomorrow, as well as on Tuesday and on Wednesday, even before our exam. So pretty much every single day between now and Wednesday afternoon, I'm going to be around. If you can't come to the office hours, or you just don't want to do it that way, of course, you're welcome to shoot me emails. And I can try to answer questions that way. Just send me an email and I'll do my best. I will be checking it every single day, probably several times a day. So lots of chances to get help if you need anything. I know you're working on learning those proofs that are in that list, the 5 theorems that I've listed. So that's obviously one thing to kind of keep cycling back to. But I would sort of rotate around between the different things that you're doing. So learning the proofs, of course, is one thing, but you don't want to just do all of that at the beginning and then do everything else and then forget the proofs later, right? You need to kind of, I think, go kind of almost in a circle, kind of keep cycling back to the material multiple times. In fact, they tell us as teachers, that's the best way to teach, is to, instead of just dumping the topics sort of linearly along, that it's actually better to sort of do a spiral approach to education and have people kind of revisiting things. So I would recommend that you guys do that too. There will be some kind of a take-home portion to the final. I decided that. I've not written the final yet, but there was almost a unanimous enthusiasm that we do that again, that people liked having that option to take something home. And that take-home part will probably, once again, like always, just be due on Friday night at 10 o'clock. I don't see any reason that I need to change that. So that's something else you can certainly be counting on. You've got a sample final to take a look at, and I would recommend tomorrow or Tuesday, whenever you feel like you're ready to give it a shot. Yeah, just sit down for a couple hours and just see how it goes. Do the best you can with that. And of course the solutions are posted as well. So there'll be lots of things to look at. There's practice quizzes, there's group works. The homework is a little much. There's too many homework problems, but you might skim through any of them, particularly on any assignment where you didn't feel that good about it. Maybe it is a sign that it would be valuable to spend just a little time looking back at some of that. And other than that, well, obviously your old midterms would be good to look at. Remember, there'll be a slight emphasis on the material. So if we ignore the proofs that you're memorizing, which are obviously fully about the new material, if we look at the rest of the exam, which would be what, 70 to 75% of the exam, of that 70 to 75%, there will be a slight emphasis on the material over these last couple of weeks in chapters 6, 11, and 13, right? Things about representing numbers as sums of squares, perfect numbers, sigma, tau, properties of those numbers, things like that. So there'll be a slight emphasis. So by that, I mean maybe 20 to 25% of the rest of the test could potentially be on that later material. And then for the first 2 midterms, I would kind of say that those should be about equal. So maybe 30 to 35% each. So out of the 3/4 of the exam or whatever, that's not the proofs, I'd say about, 35% on the first midterm, another what, 35 to 40%, another 35 to 40% on the second midterm, and then 20 to 25% on the recent material that we just learned. Does that make sense to everybody? I mean, it shouldn't make a big difference. You're going to study everything anyway, but just so you kind of have a rough idea. Okay, well, what I would like to do is some more practice problems today. And well, first of all, are there any questions about this whole deal? On Friday's review, I went through the review packet and went through everything. I don't think I'm going to do that again tonight. I think we've all looked at that. Everybody's pretty comfortable, hopefully, with what's going to happen. Remember, it's at 5 o'clock on Wednesday. I am going to let you work late, so you don't have to be stressing about rushing to get your exam done. There will be nothing like that going on. So you'll have plenty of time. Yeah, so all of that is kind of outlined in the review packet. I will be giving you the same table with all of the prime numbers that are less than 1,000, along with their smallest primitive root. That same table that I gave you on the second midterm, I'm going to give that to you again. You're welcome to use a calculator. That is totally okay. Make sure, if you've never really sat down and done this exercise, that get your calculator to do what you want it to do. If I want to figure out what the number 1,000 is in mod 234 or something like that, you might have a button that says take the mod or whatever. I mean, their calculators can do that. But if you didn't have that, maybe I should just take a moment. So if, let's say I wanted to know what is 1,000 in mod 234. So find 1,000 mod 234. If I wanted to do that with a calculator, let's say it's a very, very basic calculator. What you would do is you would divide 234 into 1,000 on your calculator. Now, when you do that, you're going to get 4 point something, 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 right? So that tells you that there's at least 4 factors of 234 that go into 1,000, but then there's also some leftover. So what you would do then is you would take 1,000 and you would subtract 4 times 234. Right? So that would be 936, I want to say. So 1,000 minus, is that 936 maybe? If I'm, yeah, 936. And so that would come out to be, what would that be? Well, that would be 64. Okay, so, that's how you would do it with a calculator. If you don't have anything very fancy and you want to just calculate what is 1,000 in mod 234, take 1,000, divide it by 234, you'll get a decimal answer on your calculator, 4 point something, something, something. So then that tells you that 4 is the multiple of the mod that you want to subtract off of 1,000. And then the remainder, after you do that subtraction, that is your reduced number in mod 234. Okay, so you can use a calculator, and if you just have a basic one, it's okay. As I said, all you really have to be able to do is, looks like a little bit of division and a little bit of subtraction. Yeah. Okay. All right, well, let me go ahead. So far, so good. Any questions? We're going to do some more practice tonight. I'm going to be doing different problems than what I did on Friday. Anybody who was here on Friday, can you tell me where we left off with which problem number it was? How many did we get through?
Oh, we're on number 6.
How many?
This is going to be number 6.
This is number 6? Okay, so we did 5 problems on Friday, so we're going to pick up with number 6 right here, okay? And I am going to be doing different problems. So if you were not here on Friday, those problems that we did on Friday are going to be worth looking at if you need extra practice because they are different, okay? So I wrote this one on the board already to get us started. Old McDonald sells chickens at $5 each and geese at $8 each. If he collects $99, how many of each bird was sold? What topic does this problem have to do with? Can anybody tell me? In the chat, Ben's got a good answer. Diophantine equations, exactly. This is basically a Diophantine equation problem. So we need to set up a linear equation, right, that models this situation. So the key step here, guys, is to notice that we have chickens and geese, and every chicken brings in $5 and every goose brings in $8. So in other words, let's just use C for the chickens and let's use G for the geese. So 5 times the number of chickens that are sold plus 8 times the number of geese that are sold, that totals up to $99 of revenue on this farm, okay? So this is a classic Diophantine equation problem. Now remember, guys, not every Diophantine equation is solvable. The only ones that are solvable are the ones where the greatest, in fact, let me write down the generic form of this. The way we wrote it in class generically, we had what? AX plus BY equals C. And the condition for solvability, so this is solvable if and only if the GCD of A and B divides C. So that's the key requirement here. And you can see here that that definitely does happen. The GCD of 5 and 8 is obviously just 1, and that divides 99. Okay, now just to remind you, what we actually have to do here is figure out how to write, a linear combination of 5 and 8 that equals 1. So I'm going to use the Euclidean algorithm for that. I'm going to take 8, I'm going to divide it by 5, which gives me a quotient of 1 and a remainder of 3. And then I'm going to take the previous divisor, which is 5, and put that on the left side and divide it by 3. When I do that, I have a quotient of 1 and a remainder of 2. And then I'm going to do it one more time here. 3 is 1 times 2, and then plus 1. Obviously, once we get down to 1, you're pretty much assured of being pretty much at the end of it. And now we just have to run this algorithm backwards, right? So we run it backwards, which means we start with 1. We're going to write it as 3 minus 2. And then we take the previous, the second line here where we have 2 and we solve for it. It's 5 minus 3. Put that into brackets like that. And I'm actually going to simplify this first. 2 factors of 3 minus 1 factor of 5. And now I have to replace the 3 by using the top equation, right? So now I'm going to take 2 times the 3 right here. 3 is 8 minus 5. And then minus 1 times 5. And one more time, I'm going to simplify that. So this is going to come out to 2 times 8 minus 3 times 5. Okay, I'm hoping this is readable. Again, I'm using my half-dead markers just to use them up here before the end of the spring. Okay, so once we've done that, then we basically have a combination of 8 and 5 that is equal to 1. Now what we're looking for is a combination of 8 and 5 that is equal to 99. So what I'm going to recommend that we do is let's take this equation here, guys, on the bottom, and let's put everything in the same order as how it's listed in this equation up here. So in other words, I'm going to take 5 and put it first times negative 3. and then plus 8 times positive 2 equals 99. Okay? Now, obviously, I've now formatted it so that, you know, it fits the notation here really nicely. The C value would be here, and the G value would be here. Of course, we have to realize we cannot have negative numbers for these solutions. You cannot have -3 chickens. So,
Dr. Anna?
sorry, yes?
Real quick. Yeah,
I
yeah,
see,
yeah.
I made a mistake. This is supposed to be a 1 over here. Is that what you were gonna say?
Yeah.
Okay, yeah, exactly. That's just a 1. Sorry, I got ahead of myself. So you can't have -3 chickens or 2 geese, obviously. And so we're gonna have to work on this a little bit. But the first thing we need to do, and now I realize what I forgot to do, is multiply through by 99. So this is easy to remember because whatever's on the right-hand side over here needs to be scaled up to a 99 on the right side. So I'm going to multiply through by 99. Now, when you do that, make sure you don't change the 5 or the 8. You want to keep the 8 and the 5 exactly as they are, like that. Okay, so let me make sure that you guys can see that okay. Is that legible? So this is a 99 over here, sorry. There we go. Okay, so this is a 190, so 5 times -297 plus 8 times 198. And that is the solution that we might call, you know, I think in the notes we would have called that X naught and Y naught. I'm going to call it C naught, G naught. So -297 chickens and 198 geese. That is a solution that does satisfy our equation. The problem is that the variables are not allowed to be negative here. So it turns out, remember, there's not just one solution to a Diophantine equation. There's actually going to be an infinite family of solutions. And let me just remind you that the rest of the solutions, so if I want to know what are all of the solutions for the variables, the unknowns, which are C and G here, you basically, of course, you have 2 slots, and you, of course, put the initial solution, the C naught, G naught in there. But then what you need to remember is that there's a plus B over D times T in the first slot and minus A over D times T in the second slot. So this is another one of those things that it's been a while since we've done this, and you just want to remember where the A goes and where the B goes, and there is a minus sign here on this one. So in this example, this would be -297, and then B over D. So the B is the, in this case, is playing the role of the 8. 8 divided by 1. So this would be -297 plus 8t, right? And then comma 198 minus, let's see, the A value is 5 divided by 1. So that's just 5, and then times t. So this is actually all of your solutions. It's an infinite parametrized family of solutions, of which only a few maybe would be acceptable here. So the key thing now is to realize that, look, -297 plus 8t, that has to be at least 0. And 198 minus 5t, that has to be at least 0. Okay, and between those two equations, we should be able to figure out what t is. So t has to be less than or equal to 198 over 5, right? So t is less than or equal to 198 over 5, but at the same time, it's greater than or equal to 297 over 8. So you can create a window of t values where you have an acceptable answer. And now from there, let's see, 297 divided by 8 is about 37 point, so this is 37.125 approximately, less than or equal to t, less than or equal to, this one is 39.6. So what that tells you actually is that there are actually two values of t that are acceptable here. T can be equal to 38, or it can be equal to 39. Just means that there are two solutions that are going to be physically acceptable on this problem. When t is equal to 38, let's see, so we just plug in 38 for t and down here in our expression, and we try to figure it out from there. I don't know if I can do that in my head. 8 times 38, and then we subtract 297 from that. Let me, somebody's probably going to have it before I do, but that's okay. 8 times 38 minus 297 is actually 7. So this would be c equals 7. And then, of course, once c is equal to 7, we can solve for g if we want to, just from this equation. So we take 99, we subtract, what, 35 from that? That should give us 64. And when we divide that by 8, we would get the number of geese would be 8. So it could be that it's 8 geese and 7 chickens. Or if t is equal to 39, then we're going to have actually 15 chickens, and we'll only have 3 geese in that case. So a couple of different valid solutions here. So is everybody good on this problem? This is how I just wanted to remind you about Diophantine equations, especially this part right here, parameterizing the infinite family of solutions. This is just a formula that we haven't seen for a while. I just wanted to put it back into your head again right here. That makes sense to everybody? We're good on that? Okay, great. I'm going to move on then. We're going to try some more problems, okay? So can I erase anything yet? Has everybody had a chance to write it all down? Okay, I'm going to go ahead and erase. Okay, so here's problem number 7. Totally changing topics. Another thing we did not talk about on Friday very much was primitive roots. So I want to talk about primitive roots a little bit. Find all primitive roots if any for n. So I'm going to give you 2 or 3 of these, I think, to think about. Okay, so for part A, we're going to do n equals 100. For part B, we're going to do n equals 32. And for part C, we're going to do n equals 27. Okay, so we'll just practice this a little bit, take a few different examples here. I'll give you guys a minute I'm not going to wait too long because I don't want to spend all night and not get through very many things, but I don't want to also steal your fun too much. So I'll just be quiet for a moment while you guys at least think about part A. So let's do this, guys. If you have your chat window open, if you have come up with an answer for part A, maybe you could type it into the chat. Don't hit enter yet. Let's let everybody type something into the chat. And then in a minute, I'm gonna have you hit your enter key, okay? I'm going pretty quick because this one, we should already be done with part A, actually. Okay, so on the count of 3, if you've come up with an answer for part A and you've got it in your chat, on the count of 3, let's just have everybody hit enter and let's see what you came up with, okay? 1, 2, 3. Okay, so, well, we don't have a great, well, actually, I forget, there's only 12 people here, so I shouldn't be expecting a lot of answers, but yeah, there are no primitive roots for 100. So there are none here. Let me just remind you again, right? N has a primitive root only if it has one of 4 possibilities, right? So recall that we have a theorem. I forget what the theorem number is actually off the top of my head. This theorem that just says that N has a primitive root. N has a primitive root if and only if 4 possibilities. Either N is 2, or it's 4, or it's a power of a prime, or it's twice a power of a prime. And here, P is actually an odd prime. Okay, so certain numbers don't have any primitive roots at all. In fact, most numbers don't, right? The only numbers that have primitive roots at all are these right here. So what about 32? Does 32 have any primitive roots? You see, it is a power of a prime, but I wanted to put this one in here because it's not an odd prime, right? 32 is 2 to the 5th power. 2 is not odd. So this one is also none. Okay. So by now you've probably figured out though that 27 does have primitive roots. It's just 3 cubed, and that is just a power of an odd prime. Now remember that the number of primitive roots, we have a nice formula for that. And the answer is phi of n. So a lot of people like to jump straight to this equation, but the thing is you got to make sure that there are primitive roots at all in the first place. So you don't want to be doing phi of n on parts A and B here, just on this part C that we're looking at right now. So this is actually phi of, let's see, 27 is 3 cubed. So remember, we have a formula. This is another theorem that we learned. Phi of any prime power, phi of a power of a prime is just that power minus the one smaller power. So p to the k minus p to the k minus 1. So in the case of 27, we're simply going to take 3 cubed minus 3 squared. That would be 27 minus 9, which is 18. And now we have to figure out phi of 18. And remember that phi is multiplicative, so I can write it as phi of 2 times phi of 9, split up the prime factorization of 18. Phi of 2 is just 1, and phi of 9 Well, 9 is just 3 squared, so we can just take 3 squared minus 3, and we get 6, right? 9 minus 3 is 6. So there should be 6 primitive roots, and we're supposed to find all of them. Let's just recall the definition, right? R is a primitive root. R is a primitive root if the order in mod n of R is phi of n. That's the definition. We're going to practice some things with order in a little bit as well, because I think there's still some room to improve on that. The order is the smallest power of R that is congruent to 1 in mod n. And by Euler's generalization, we know that at the worst case, the phi of n power of any element that's relatively prime to n, the phi of n power of A would be congruent to 1 in mod n. We know that for sure. That's not what's exciting here. What's exciting about a primitive root is that its order is not any smaller than phi of n. Okay, so we're going to now try to look. Oh, and by the way, in your table that's going to be on the front of your exam, you'll have an example of a primitive root for any prime number. I'm specifically choosing a number here, 27, which is not a prime. It's a prime power. So in this case, we actually have to do this work now. We can't just say, oh, I'm going to look in the table and find the answer. But if n was a prime, let's say that n was 37, which is a prime, then what you could do is you could go to the table, which is going to be on your exam, grab the smallest primitive root for 37, and then use that to generate all of the other ones. Like, this is the strategy that you can use. Once you find one primitive root, we can get all of the others. And I'm going to review that with you right now. Okay, let's come back over here. Just let me know, guys, if there's any questions here as we go along. I'm looking to come up with 6 primitive roots for the number 27. So in other words, we are seeking, we are going to seek these numbers, I'll call them A, such that the order of A is phi of 27. We already worked that out. That was, I believe that was 18, right? So we're looking for numbers that are of order 18. Now the possible orders, '18 is the largest possible order for any number in mod 27. But there is a possibility, of course, that some numbers could have smaller orders, such as, for example, 1 is a possible order, or 2, or 3. I'm looking at the divisors here of 18. Right? So the possible orders of any element are always just the divisors of phi of n. This is helpful because it means that if you're trying to test a number to see what its order is, you don't have to take every power of that number. You only need to look at these powers. Okay? And also remember that if a number is not relatively prime to 27, it doesn't have an order to begin with. So anything that's a multiple of 3 is pretty much out. We're not even going to look at it. So the numbers that we are seeking are going to be relatively prime to 27. And it doesn't really matter where we start, but let's just try a number. Let's just choose a candidate here. Let's just choose, I don't know, let's just pick the smallest number that has a chance. right? A has 2 has a chance of having order 18. What we need to do is we need to calculate these powers of 2. And 2 to the first, 2 squared, 2 cubed, right? And maybe even, 2 to the fourth. Well, we don't want 2 to the fourth. But let's say 2 to the sixth, which is just 64. None of those are congruent to 1 in mod 27, right? None of those are going to be congruent to 1. They're, you can just calculate 2, 4, 8, and 64. It's pretty obvious. So the only other possibility is that it has order 9 or that it has order 18. Let's just look at 2 to the 9th. Now 2 to the 9th is 512, and that's perfectly fine if you just want to take 512 and reduce it in mod 27. But I'm just going to try and be brave and do it without a calculator. I'm just going to break this down as 2 to the 6th times 2 cubed. Because in theory, I already would have looked at 2 to the 6th, which is 64. 64 in mod 27 is actually just the same as 10. And 2 cubed is just the same as 8. And so this comes out to 80, which is actually congruent to -1. So in other words, it is still not congruent to 1. So we have actually ruled out 1, 2, 3, 6, and 9. The order of A has to now be 18. We don't have any more doubt about that, right? If it's not 1, if it's not 2, if it's not 3, if it's not 6, and if it's not 9, then it has to be 18. So thus, what this shows, if you guys are with me, what this shows is that 2 is a primitive root of 27. Now we kind of got lucky here because the very first number that we tried worked. If we had come up with a smaller, like if the order of A had been less than 18, then we would have to just go on and try a different number. So you'd probably choose 4 next, right? 4 would be the next logical choice. And just keep going like that. But in this case, we don't have to go any further because we found a primitive root. The nice thing now, guys, is that all of the numbers that are relatively prime to 27, there's 18 of them, right? Phi of 27 is 18. Those 18 different numbers that are relatively prime to 27, they are all just powers of this primitive root. After all, you get 18 different values, don't you? You get 2 to the first, 2 squared, 2 cubed, all the way up to 2 to the 17th, and then finally 2 to the 18th is congruent to 1 again. This is actually a set of representatives for the congruence classes of the non-zero congruence classes of mod 27. For the, I'm sorry, not the non-zero ones, the relatively prime ones. So, does that make sense? The other 5 primitive roots for 27 are in this list. This is a comprehensive list that tells me all of the 18 numbers that are relatively prime to 27. So what I can do is start taking powers of this. Powers of this primitive root, and we have a formula. Let me remind you, this is theorem 8.3. I happen to remember that theorem number. That actually tells me the order in mod n of A to the H. You remember this? There's a nice formula for this. This is one you will definitely want to know this one, right? This is going to be the order in mod n of A divided by the GCD of the order in mod n of A with this exponent H. Okay, is this legible? You guys read this okay? Hopefully my H's and my N's don't look the same. So in this case, if we plug in 2 for A, we already know that the order of 2 is 18. So I'm just going to put in the 18 there, and I'm just going to divide this by the GCD of 18 with H. So this is a fraction. It's just 18 divided by the GCD of 18 with H. So if I would like to find my other primitive roots, I want this denominator to be equal to 1, right? So in other words, we would like the GCD of 18 with H to be equal to 1. Set that equal to 1 basically. And that tells me that H, well, there are 6 different H's that are relatively prime to 18. That's the phi of n, right? So H could be 1, of course, or it could be 5, or 7, or 11, or 13, or 17. Okay, so out of all of these powers of 2 that we have up here, the ones that are the primitive roots, in this example, the ones that are the primitive roots are just 2 to the 1st, 2 to the 5th, 2 to the 7th, and so on. So the primitive roots okay, so the primitive roots would be just this. We would have 2 to the 1st, 2 to the 5th, 2 to the 7th, 2 to the 11th, 2 to the 13th, and 2 to the 17th. I can't really think of a reason why you would need to simplify these expressions, but if you ever wanted to, of course, it's not that hard to do with a calculator. Even 2 to the 13th power, right? Some of these are really easy. 2 to the 1st is 2. 2 to the 5th is 32. And of course, I'm reducing that in mod 27, right? And then I keep going like that. 2 to the 7th would be 20, I guess. And so on, right? So I'll just let you guys, if you're interested, you can calculate the rest of those. Does this make sense? The only numbers that even have a chance of being primitive roots are the ones that are relatively prime to 27. So that's why I started with A equals 2. And if that had not worked, I would have skipped over 3 because 3 is not relatively prime to 27. I would have gone on to 4 and then 5. 5 turns out would have worked, right? And then I would have skipped over 6 because 6 is not relatively prime to 27. So if I really wanted to, if I had to like keep searching for that first primitive root, that's what I would do. I would just try these numbers that are relatively prime to n until I find one that has the right order. Make sense? Okay. Can I erase? I want to go on if everybody's okay with this. All right. On the second midterm, there was a little bit of problems. There's still some problems on the second midterm about the concept of order. So I made up another practice problem that's similar to one that you did on the second exam. And I want to work through this if that's okay. So this is number 8, I think. So let's let P, Q, and R be distinct primes. Okay, so we take 3 distinct primes. Let's just assume we do that. And then let's assume, I'm sorry, 3 distinct odd primes. I want to make this as simple as I can. 3 distinct odd primes. Okay. By the way, on the test, if you get one of these sort of more abstract problems, there's nothing wrong with tinkering around with it by trying an example. If you wanted, you could think of some numbers here. I don't know, 5, 11, 23, something like that. Pick 3 distinct odd primes. And then let's assume that the order in mod R of A is 2p, and the order in mod R of B is 2q. Okay, then what I'm going to try to do is prove that the order in mod R of AB is 2pq. So it's actually, you do not just multiply the order. So you don't take 2p times 2q. It's actually 2p. So it's essentially the sort of like the least common multiple of the individual orders. That's essentially what's going on here. But I just want to prove this as an example. You had a midterm 2 question that was very similar to this. And there were some missing steps that some people didn't quite get the whole thing down. So I would just like to go through this and make sure everybody understands what's involved. Remember, guys, the order of an element is the smallest positive power of that element that is congruent to 1 in mod n. In this case, the modulus is a prime itself, which is r. Okay, so that's something to keep in mind. Okay, so for the solution to this is more of like a proof problem. There's sort of 2 parts to this. The first thing is I have to prove that if I take AB and I raise it to the 2pq power, that I do in fact get 1 out of that. So let's just try that. So if I take AB to the 2pq, and this is all happening in mod R over here. Get my modulus written down. Can anybody suggest maybe the first step here? What would you do with the algebra maybe?
Split it, so it's A to the 2pq times B to the 2pq.
Exactly. Very good, Renee. Exactly. That's exactly what I had in mind. You're just going to take this and write it as A to the 2pq times B to the 2pq. Okay, we certainly can do that. Just split it up. And then, you see, we already know that the order of A itself is just 2p. So I can think of this as A to the 2p raised to the q, and then similarly B has order 2q. So if I raise B to the 2q and then put p, right? So I just kind of organize my exponents a little bit. Then what I have is actually just 1 to the q times 1 to the p, which is congruent to 1. Okay, so this is a multiplication right here. Right, so, and this is all in mod R. I ran out of room to write that down again, but let me just put it here.
Dr. Annan?
Whatever the modulus is. Okay, so guys, are we done?
Dr. Annan, real quick, the mod R, are we supposed to be working in mod PQ or something like that?
No, this is just in some other big mod. I don't really care what the mod is.
But then since R is a odd prime, doesn't that mean like the order of an element in R has to be like,
Well, so in mod
yeah,
n, right, the orders of all of the elements would have to divide phi of n. So in this case, phi of r would be, if r is a prime, it would be r minus 1. So I'm making an assumption in the background, which I don't want to worry about too much, which is the assumption here is that 2p does divide r minus 1. And 2q does divide r minus 1. R minus 1 will be even. And I'm just assuming that the p and the q are such that they do divide into that. Does that make sense?
right, okay, thank you.
Yeah, sure. So there's an assumption here, right? Remember, there's only certain values that are possible as the order of an element. The order of an element always has to divide phi of n. And in this case, my n is this prime number r, and phi of r is just r minus 1. We know that. So we're assuming here, even though I didn't really state it, we're assuming that 2p and 2q both divide into r minus 1. Excellent. So am I done here? Is this all I have to do?
No,
This will get you some partial credit, but it's definitely far from done, because this doesn't convince me that the order of AB is 2PQ. The order actually could be smaller than 2PQ. Now, for sure, what we can say is we can conclude now that the order in mod R of AB is definitely a divisor of 2PQ. Right? In other words, 2PQ has to be a multiple of the order. Which powers of an element are congruent to 1 mod n? Well, they are just those powers that are multiples of the order. So I do know, I'm trying to prove that the order of AB is equal to 2PQ. Right now, all I know is that the order divides 2PQ. So what are the possibilities here? So this implies that the order in mod R of AB, let me actually just list out what are all of the divisors of 2PQ. We've got 1, we've got 2, we've got P, we've got Q. What else? We've also got 2P, 2Q, PQ, or 2PQ. Those are all of the possibilities for the order of AB right now. Okay. Well, this is the one we want over here on the very end. So what I'm going to hopefully do right now, guys, is convince you that all of the other answers are wrong. Okay. So we're going to try to do that. So for example, could the order, let's suppose that the order in mod R of AB, let's just pick one of these to start with. It's fairly easy to analyze. Let's just take P. Right? Well, actually, I'm sorry. Let's take 2P. Let's start with 2P. I'm going to try to cross 2P off of my list. Let's start with 2P. I think this is the best one to start with. Now, on the test, you may not be thinking of this exactly the way I'm thinking of it. That's okay. There's, I happen to be picking 2P out of this stack of choices right now. But you don't have to necessarily do that. Like, you can kind of start anywhere and make some observations as we go along. So let me just show you what this would tell me. This would tell me that, you know, AB, well, obviously, AB to the 2P is congruent to 1 mod R. Right? And because the order of A itself is 2P, we actually already know that A itself to the 2P power is already congruent to 1 in mod R. So if you just break this down, this becomes A to the 2P times B to the 2P congruent to 1 mod R. But if I put in 1 for the A part, A to the 2P is 1, right? So then if I put a 1 in there for that, then that tells me that B to the 2P is congruent to 1 in mod R. Anything wrong with that?
2P doesn't divide 2Q. Or
Yeah, the P and the Q are distinct primes, and so well, what this would actually imply, is that the order of B, which is 2Q, has to divide 2P. Right? So any power of B that is congruent to 1 has to be a multiple of the order of B. And this is a contradiction right here, because if I just, basically this tells me that Q divides P. You can just take out a factor of 2 on that equation. And Q dividing P is impossible. So I'm going to cross off 2P from being the order. Okay. But you know what? That actually allows me to also cross off some other things. If the order is not 2P, then if the order, just by the same kind of reasoning, if the order of AB was just equal to P, if it was just P itself, then you see, we can just start right here. AB to the P is congruent to 1. And that would imply that we can go right back to where we were a moment ago and put 2B there. So in other words, we could just square both sides of the congruence. So is that readable? I can't tell. I know it's a little dark in here tonight. And I've got a bit of a old marker with me. So this would imply that AB to the 2P is congruent to 1 because you're just squaring both sides of this. And now you're right back in the same dilemma that you were before, right? You get the same exact, you end up in the same exact place, Q dividing P again. So in this case, we can rule out that the order of AB is equal to P as well, right? So basically you're going to, from here, you're just going to follow these same exact steps. So we can cross off, I already did. We have what here? 1, 2, P, Q. There we go. So I'm going to cross off P. And I can cross off 2. Because again, if AB squared, right? So in other words, if I came in here and put a 2 here, then again, I could put a 2 here and then take the Pth power of both sides and I get to the same work again. Actually, any divisor of 2P can be crossed off. The order also cannot be 1. The order of AB cannot be 1 because if it was, I would just take this equation, power it up to the 2P power on both sides, and then come over here and trace through the same work again. All of these numbers are getting crossed off. And then similarly, go back up to the top to make another observation here. Similarly, for 2Q. So if the order, well, let me write it out exactly what I mean. Similarly, for the order of A, B equal to Q, that's also a contradiction. So I'll cross off 2Q as well, which means I also get to cross off Q. So this is, sorry, 2Q. So if the order of AB was 2Q, we just run through the same exact reasoning. We get the same exact contradiction essentially. And same thing for Q. So I have now crossed off everything except for PQ. Okay. So let's talk about PQ for a minute. So consider AB to the PQ power, right? I do know that this number satisfies x squared congruent to 1 in mod R. I do know that, right? Because if I take AB to the twice PQ power, I do get 1 in mod R. Now, the thing is, because R is a prime, this is a quadratic equation. How many solutions can this quadratic equation have? What if I'm in mod of a prime? It's Lagrange's theorem.
At most.
Yeah,
two.
at most 2, right? It's at most 2. If the modulus is not prime, all bets are off, right? If the modulus is not a prime, you can have polynomials of low degree that have tons of solutions. But because R is prime, this congruence can have at most 2 solutions. So by Lagrange's theorem, this implies at most 2 solutions. Well, I actually know what the solutions are, don't I? Can you tell me what the solutions are here? X squared equals 1. What are the solutions?
It's x and negative x.
X squared equals 1. What are the numerical values of the solutions?
1 and negative 1.
Exactly. 1 and negative 1, right? So we actually already know that AB to the PQ is congruent to 1 or to negative 1 in mod R. Those are the only possibilities, right? So AB to the PQ is congruent to either 1 or negative 1. Now, here's the thing, guys. Do we know what A to the P itself is congruent to in mod R? Do we know what goes right here?
-1?
Yeah, it has to be negative 1, doesn't it? Because remember that we know that it's the same reasoning. We already know that A has order 2p, right? So I'm just going to scribble for a minute. A to the 2p power. This is maybe a little hard to see. Let me write this over here. So we know that A to the 2p is congruent to 1 mod R. And so again, by using the same Lagrange's theorem, A to the p satisfies the same quadratic equation, which means that A to the p is congruent to 1 or negative 1. But it can't be 1. This cannot be congruent to 1, guys. Because if it was, the order of A would be only P, right? Or at most P. It wouldn't be 2P in that case. So A to the P is a small enough power of A. We're really practicing this concept of order right now. This is why I wanted to do this problem, right? If we raise A to a smaller power than its order, we cannot have 1 yet. So this A to the P, technically there are 2 choices, +1 or -1, right? Because it satisfies this quadratic equation. Right? And most 2 solutions are plus and minus 1 here. Right? So anytime you got a solution in a prime modulus to this equation, its solution is either 1 or -1. Technically, those are both possible. But because the order of A is 2P, this one has to be -1. It has to be -1. And similarly, B to the Q has to be -1. So now if I take that information and I look at AB to the PQ, let's do what we did before, right? Let's write this as A to the P to the Q times B to the Q to the P. And what are we going to get? This is A to the P, that's -1 to the Q. And then we have P. And guys, P and Q are both odd. So you have -1 to an odd power, you have another -1 to an odd power. That means you have actually a +1 over here. Right? This would be in mod R, sorry. You know what that shows, guys? That shows that I screwed up. We need to go back to I just made this problem up 5 minutes before the review. And I screwed it up. Go back to where I started writing the question down. I said, assume that the order of A is 2P. Assume that the order of Q is the order of B is Q. And I said, prove that the order of AB is 2PQ. Please erase the 2. What we've actually proved now is that the order of AB, this actually proves that the order of AB is actually just PQ. We found a smaller power of AB that is actually congruent to 1. So that's just a oversight on my part. It was supposed to be order of P times Q. Okay, but does the idea behind this make sense, guys? I am probably going to ask about order again on this exam. The second midterm, there were enough people that were not checking that the power was the smallest power before they were concluding that something was the order of something. So remember, the order, there's 2 parts to it. First, you have to prove that when you raise the element to what its order is supposed to be, that you do get 1. And then you also have to show that no smaller power would have worked. It's kind of like for those of you who've taken real analysis already. If you're trying to prove that something is a supremum of a set, you have to prove that it's an upper bound for that set, but then you also have to prove that it's the least upper bound for the set. So there's sort of 2 parts to that as well. Same thing here. You prove that the power that you want works, but then you also have to prove that no lower power works. Okay, great. I just wanted to try that one out on you guys. Okay, are you ready for another problem?
Dr. Annan, I have a quick question on this one.
Please.
So, you said just to erase the 2 on the last part, the order of.
Well, what I mean is on the statement of the question 10 minutes ago, when we wrote down the problem, I said prove that the order of AB is equal to 2PQ. That should just say PQ.
Okay, and then So if we continue it the same way we did before, how would we show that? So how we started showing that AB to the 2PQ is congruent to 1 mod R? Would that change? I mean, how will that change without the 2?
I know what you're trying to say. Do we have to work? So now the only possible orders would be divisors of PQ, which would be 1, PQ, or PQ.
Okay,
And
so if we do this again, we wouldn't be able to show that right from the beginning that AB to the PQ is congruent to 1. Like
oh no, we could have done this first, right? We could basically have done this part first.
yeah, sorry, but I mean with the 2P and the 2Q, that's what's kind of me a bit.
Yeah, I probably should just go back and take all of the 2s out.
Okay.
I was trying to be creative because I think I've asked you a question before where there was no 2s in it. So I wanted to try to make this a little bit different, but I think you're right. I probably need to go back and fix things a little bit. And just probably the best thing is to just assume that the order of A is P and the order of B is Q. And just let's take all of those out of everything.
Okay.
Does that make you happier if we do that?
I mean, it makes more sense to me.
I mean, that's the concept I'm trying to get at with this problem. So I'm not trying to like sort of hide the essence of what's going on here. And so I think that factors of 2 are not helping us to really get the idea. So yeah, I would just take out the 2s.
Okay.
Yeah, this is very similar to the problem we already did on the midterm, actually, which isn't bad to review because a lot of people did have trouble with it. But anyway, I just wanted to kind of go over this again. So guys, the order of an element is the smallest power of that element that is congruent to 1. As a nice little mention of the Lagrange's theorem here, which I think is really cool too. Okay, any other questions on this one? I know I botched it up a little bit, but the main idea of it, of what I wanted you to be thinking about with this problem is definitely here. And we definitely talked it through. Okay, great. Let me go ahead and erase this. Let's try another one. Okay, so this is number 9, I believe. I'm going to let P be prime. I want it to be at least 7. And I want to try to prove that the Legendre symbol, so here we're going to do some Legendre symbol practice now. The Legendre symbol of 15 in mod P is equal to 1 if and only if P is congruent to plus or minus 1, plus or minus 7, plus or minus 11, or plus or minus 17 in mod 60. So it's a bit of a big modulus here, mod 60. The reason that the mod gets that big is because you've got 15 here, right? 15 is 3 times 5. But then there's something about this quadratic reciprocity that involves looking at mod 4. Remember that? So for example, when you flip the Legendre symbol over, it costs you a minus sign only if the number on the top and the bottom are both congruent to 3 mod 4. So there's actually a mod 4 business that comes into this. So that's why this turns out to have a number of little cases. So the way to do something like this, and there was one like this on the second exam, so I just want to practice this as well because a lot of people got this right, but a lot of people were also taking it home. I think this was the most popular one to take home on the second exam. The thing to realize here, first of all, guys, is that you cannot flip this Legendre symbol over as is. Remember that when you flip things over, both the top and the bottom have to be odd primes. Otherwise, you cannot do that. So the first step is actually to break this up as Legendre symbol of 3 in mod P times the Legendre symbol of 5 in mod P. So you break this up into a multiplication. So that's one of the properties of the Legendre symbol. Again, don't go showing this algebra to your young kids. You'll destroy their math, their faith in math. It looks like there's a p squared on the bottom now, but no, that's not the way this notation works. Okay, so what I'm actually going to do, in order to get a 1 right here, either both of these are 1 or both of them are -1. So I'm going to actually examine the individual factors here. I'm going to do them separately to start off with. So for instance, let's come over here and work on the Legendre symbol of 5. Now, in the case of 5, this is actually the easy, I'm starting with the 5 because it's the easier case. That's because 5 is already what? Congruent to 1 in mod 4. So you get to flip this one over no matter what P is. It doesn't even matter. This one flips over. That just always flips over because 5 is congruent to 1 in mod 4. If we were working with 3 on top, then we have to think about cases there. But for right now, this is all we have to think about. And under what circumstances, let's actually write out when it's equal to 1 and when it's equal to -1. Remember, if this is equal to 1, it means that it's a quadratic residue. So what we're asking about right here, guys, are the quadratic residues in mod 5. Well, that's easy enough to figure out. You just take 1 squared and 2 squared and you're done, right? You don't actually have to go past, you guys proved in the homework that all of the quadratic residues are covered by the time you go up halfway to P, basically, P minus 1 over 2. So if I take 1 squared and 2 squared, that's it. And that's 1 and 4. So the quadratic residues would be the numbers that are congruent to 1 or 4, and I'm going to write that as plus or minus 1. This is, of course, in mod 5. And we get -1 if P is congruent to plus or minus 2 in mod 5. Okay, so at least in mod 5, I know, whether 5 is a quadratic residue in mod P or not. It's just flip this thing over, right? And these are your quadratic residues. I'm basically brute forcing the quadratic residues. I'm just literally squaring every number and just seeing which results come out of that. And the results that come out of it, when I reduce them in mod 5, they are either 1 or -1. And I don't ever get 2 or -2. So now 3 is more interesting. Let's actually start with just the Legendre symbol of P in mod 3. I want to look at this first, and then we'll worry about flipping it over. So let's take this 3 and P. No. I'm sorry. Let's start with, I wrote it right the first time. P and then a 3 on the bottom. Let's start with this one. Sorry about that. So I want to figure this out first, and then I'll worry about flipping it over. Obviously I need to have it flipped over here eventually, but let's just work on this first. This is pretty easy to figure this one out because, again, we're just looking for the quadratic residues in mod 3. So mod 3 is so small. All I have to do is square 1, and that's the only one that gives me a quadratic residue. So this is just if P is congruent to 1 in mod 3. And -1 if P is congruent to 2 in mod 3. That's basically it. It's just, that's pretty easy. The problem comes in that we want to flip over this result to get the Legendre symbol of 3 in mod P. And what we need to keep in mind here is that the Legendre symbol of 3 in mod P, right? It's either equal to, well, it's either, let me just do it this way. I'll make another big brace here. It's the same as the Legendre symbol of P in mod 3, only if P is congruent to 1 in mod 4. Right? If P is congruent to 1 in mod 4, then you get to flip this thing over, there's no problem. However, there is a sign change. I have to change the sign on this and put a minus in front of that. Oops, that's minus of the Legendre symbol of P with 3. And this would be if P is congruent to 3 in mod 4. There we go. So now I want to try to paste this together. Let me come back over here again. I want to just figure out, all right, so when is the Legendre symbol of 3 1 and when is it minus 1? Like, I need to sort of summarize this now. See what I'm doing? Is everybody with me? So the question is sort of like, how could I end up with a 1 up here? Like, how could this be a 1? Well, one choice would be if it was 1, if this one was 1 and there was no sign change. So in other words, if we were in this case together with this case, right? Now, in that situation, we'd end up with a 1 over here. Well, what is that situation? Well, that's where P is congruent to 1 mod 3 and P is congruent to 1 mod 4, which if you want to use the Chinese remainder theorem, you can, or you can just mentally figure it out that if P is congruent to 1 in both mod 3 and in mod 4, then it's also congruent to 1 in mod 12. So this would be if P is congruent to 1. Leave yourself a little bit of room because we're going to need to add a little bit more to this yet. But mod 12, I'm taking the mod 3 and the mod 4 and I'm working it up to mod 12. But you see, there's another way to end up with a +1, which is that I could have a -1 here, P congruent to 2 mod 3, and then I could have a sign change down here. So if I have this -1 together with a sign change, now what is that? P congruent to 2 mod 3 and 3 mod 4. You guys can check that that's actually -1 in mod 12. So I'm going to write plus or minus 1 right there. Okay. So if P is plus or minus 1 in mod 12, then that's the conclusion. And then how do we end up with a -1? Well, that would be either P is congruent to 2 mod 3 and no sign change. So P congruent to 2 mod 3 and P congruent to 1 mod 4. If you put that together in mod 12, it's 5. So this would be if P is congruent to 5 in mod 12. So that's taking this case with this case, right? So there's a minus sign here, but not here. The other option, of course, is that you could have a +1 up here and then a sign change down here. So P congruent to 1 mod 3 and P congruent to 3 mod 4, that actually means that P is congruent to 7 in mod 12. And I'm going to write that as +4 minus 5. Okay. And by the way, those are the only number, there's only 4 numbers that are relatively prime to 12. If P is a prime, it's definitely relatively prime to 12. So that would be 1, 5, 7, and 11. Those are the 4 different primes. 2 of them give us a +1 right here, and 2 of them give us a -1 right here. Are folks with me out there? I figured out the Legendre symbol of 3 in mod P. I also have the Legendre symbol of 5 in mod P. Now I want to get 15. So now I'm going to put those together under multiplication. So let's see if we can do it. 15, the Legendre symbol of 15 in mod P. Well, let's just figure out how it could be equal to 1. Well, actually, let's just do it the way we did the other one. Let's just make a brace here. And let's just do the plus and minus 1 case. So we could get a 1 here, or we could get a -1. Those are the possibilities. Let's see if we can figure this out. Well, either both of these are 1, or they're both -1 in order to get on the first line. So how are they both equal to 1? Well, let's see. We've got just 4 possibilities. Oh my goodness. P is congruent to 1 or -1 mod 12 and 1 or -1 mod 5. Let's just write that out first. So this would be if P is congruent to ±1 mod 12 and ±1 mod 5. That's one possibility. Oh boy, I need more room though. Or there's another way that we can get a +1, which is that we could get a -1 here in this symbol and a -1 over here. So, or if P is congruent to, so what would that be? ±5 mod 12 and P is also congruent to ±2 in mod 5. You guys with me? See, for this to be a plus, I didn't even get to the -1. I ran out of room. The +1 case is either +1 right here and +1 right here, or it's -1 right here and -1 right here, right? 1 times 1 or -1 times -1. Do you see that there are actually, how many different cases do you have? There's 2 choices here, 2 choices here, 2 choices here, 2 choices here. Like I can make 4 different combinations here, and I can make 4 more combinations here, which is actually 8 combinations. If you look at the answer up here, you see there's 8 different answers. So we can pretty much finish it by just looking at those cases. So, case 1 might be, well, this would be the easy one. P is congruent to 1 mod 12 and P is congruent to 1 mod 5. That's one possibility, that we have a 1 here and a 1 here. Or we can have case 2, Case 2 might be what? P is congruent to 1 mod 12. And it's congruent to -1 mod 5. Be another possibility, right? And then you can keep going like that. I'm not going to maybe do all of the 8 cases right now, but just you're getting kind of the idea, I think. Let's just write down another one at random. There's one case down here on the bottom section, P congruent to -5 mod 12. And so I'm not doing these in order anymore. I'm just trying to list something that might be interesting. P congruent to 2 mod 5. Let's just take that case. So there's 8 cases in total if you work them all out. And if you work mod 12 and mod 5, the Chinese remainder theorem gives you a result in mod 60. So like right here, this is gonna, the case 1 is just going to give me P congruent to 1 mod 60. Right? Something like that. And then let's see about case 2. We need a number that's congruent to 1 mod 12 and -1 mod 5. Does anybody have an answer? I don't think I know this answer off the top of my head. It's not going to be 13. It's not going to be 25. It's not going to be 37. It's going to be 49. 49. 49 is congruent to 1 mod 12, and it's congruent to -1 in mod 5. 49, which is the same as -11. It's the same as -11. Right. How about this one down here? P congruent to -5 mod 12 and congruent to 2 mod 5. Oh, that's an easy one. That's actually just 7. This one would be P is congruent to 7 mod 60. If you just go through the 8 cases, guys, if you just go through the 8 cases, you're going to get the 8 different choices that are here in this list. Now, is this making sense to everybody out there? I'll just say ... Because I don't think we need to write them all out. I think you have the idea here. We're just combining, there's 4 cases here, there's 4 more cases here. That gives you all 8 cases. You're going to enumerate exactly the 8 choices of P that you have here. Now, what I've learned my lesson, and this was totally my fault, has nothing to do with you guys, but I had one of these on the second midterm, and it's just entirely too long. To try to do this during a test is really too long. I have learned my lesson from that. I like this problem. I really do. You see, I've got at least one in the group work. There's one in the practice quiz. We had it on the midterm. It's something I keep talking about. I like this analysis that we are doing here. But what I would probably have to do is find a way to narrow this down so that you're not having to do 8 different cases here. And in fact, if you were looking at the Legendre symbol being equal to -1, that would actually be 8 other cases. So now you would end up with like 16 things to check, and it's just a little too much. So what I would probably try to do on the test is I might say something like this. Prove that if P is congruent to -11 mod 60 or 7 mod 60, then the Legendre symbol of 15 in mod P is congruent to 1 or is equal to 1. Right? I might actually specifically force a particular case, and then you don't have to do 8 cases. You would just have to do 1 case. So I think that's a more likely scenario for me to ask you to analyze something like that. But I wanted to still go through this in full because, or at least setting it up in full so you could see how do you really want to break something like this down. Are there any questions on this?
So if you ask us this question on the test, like the way you said you were going to, how do we
Yeah.
go about solving it? Because I know like right now we're like trying to figure out what it's congruent to, and it was taking like some guessing. So like, what would
So
be
if I said, tell me what the Legendre symbol is for 15 in mod P, where P is congruent to -11 in mod 60. There's a couple of things that you could do. One is you could actually just pick a number that actually satisfies that. So like, let's say I said P is congruent to -11 mod 60. If you wanted, you could do something like this. You could say, you know what? I happen to know that 109 is a prime. And so you'd be able to just work this out and come up with 1 or -1, and that would be, you know, your answer. Because it's all just comes down to congruence in mod 60. Just as a little tip, you could just do this. However, the whole idea would really be, what I would really want you to do is the following. So if I ask the question like this, assume P is congruent to -11 mod 60. Prove the Legendre symbol of 15 over P is 1. If I asked it like that, what you would want to do would be to break it down, break 60 down. So 60 is 3 times 4 times 5. So then this tells me that P is congruent to -11 in all of these individual mods, right? If 60 divides something, then so does 3, 4, and 5. Right? So you could think of it this way. And okay, well, in mod 3, -11 is the same as +1. So P is congruent to 1 mod 3. And then in mod 4, -11 is also congruent to 1. And then in mod 5, -11 is actually congruent to -1. So you would break it down into mod 3, mod 4, and mod 5. And then what you could do is you could say, all right, well, now let me work on the Legendre symbol. So then what I could do from there, now what you would do is you would say, okay, the Legendre symbol of 15 over P is equal to the Legendre symbol of 3 over P times 5 over P. And now you just start, you say to yourself, okay, since P is congruent to 1 mod 4, I get to flip both of these Legendre symbols over. So this becomes the Legendre symbol of 3 in mod P times the Legendre symbol, P in mod 3 and P in mod 5. So no sign changes there because P was congruent to 1 mod 4. So I flip it over like this, and then I say, okay, if P is congruent to 1 in mod 3, then this is equal to a 1. And if P is congruent to -1 in mod 5, well, that's also a quadratic residue in mod 5, so that's also a 1. Sorry, this marker is really, that's 1 times 1, which is 1. Ben, does that answer your question?
Yeah, it does. Thank you so much.
This is how I could phrase it to be just like one case now. I say, assume that P is congruent to this number, mod that, prove this thing. And now you don't have to analyze every scenario. You're just analyzing the one scenario that has these congruence values in mod 3, 4, and 5.
Can you, why was P over 5? Why was that 1 and not -1?
Because what are the quadratic residues in mod 5?
1 and 2.
Well, how about 1
Right.
squared and
Yeah,
2
1 squared.
squared?
Okay.
Right, so when you're finding the quadratic residues, you're just literally squaring all the numbers. So in mod 5, if I take 1 squared and 2 squared, I get 1 and 4. But 4 is the same as -1. So if P is congruent to -1, it is a quadratic residue. That's why this is a +1. If this had been a 2 or a -2 right here, Jamie, then we would have put a -1 right there.
Okay, thanks.
Yeah, good question. Like if I changed this problem a little bit, I could have chosen a different value here besides -11, and maybe I'd come up with a -2 right here. Yeah, then things would get more interesting because you'd end up with a -1 right here, and the answer overall would be -1. Yeah. Okay, so anyway, those are kind of good to practice. Another thing, of course, to be able to do, let me come up to another problem here. Another thing to be able to do, guys, is to just work through one of these. This is probably a little bit easier, but I just want to do it because I haven't reviewed it Friday or today so far, which is just this problem here. I think, am I on number 10 now? Is this number 10?
Yeah.
Okay, great. Let's just practice one of these. Let's just compute the Legendre symbol of 182 in mod 421. When I write something like that down, of course, you can assume that the number on the bottom is a prime. And so in this case, 421 has to be, otherwise it doesn't make any sense. So the 421 has to be a prime, but the number on the top is obviously not a prime. So what do you think I'm going to want to do first here, guys?
Break it up to its prime factorization. So 2 times over 421.
Yeah, Renee, you're doing great. Go ahead. So 182 breaks up as 2. And then what else do we have?
91.
91, right? 2 times 91, but 91 is not a prime. It actually factors as 7 times 13. So I'm going to write this as 7 over 421 and then 13. So yeah, I think just prime factorizing your expression to start off with is a great way to get started. Let me just remind you guys that we have a nice formula for the Legendre symbol of 2 in any prime. Right, so this is a theorem. I think it's theorem 9.6. So this one is going to be worth just knowing this so that you can use it, right? The formula here for the Legendre symbol of 2, we actually did prove this, is 1 if, what was it? P is congruent to plus or minus 1 in mod 8. In other words, it's 1 or 7. And if P is plus or minus 3 in mod 8, so it's a mod 8 thing. If it's plus or minus 3 in mod 8, then we get the -1 out of it. So we actually will need to look at our 421 here and think about it in mod 8. So you can check, obviously 400 is a multiple of 8. Without even having to think too hard, we can kind of just see that 400 is a multiple of 8, which means that 421 in mod 8 is actually just the same as 21. And 21 in mod 8 is actually just 5. So I'm just going to make that as a note. I know I'm going a little fast doing some mental calculations here, but I'll let you guys check this later if you need a little more time. But 421 is congruent to 5 in mod 8. And so we're in the case, the bottom case here. So this Legendre symbol, this one is going to be -1. Whoops, I need to just give myself more room. Let me come over here to the left. So we have a -1. And then what do you suggest that I do with the other two Legendre symbols? I see people using their hands to suggest flipping these things over, right? We can flip them over because they are both odd primes. Yeah, so we can flip, let's do that. Let's flip over 421. Oh, but we have to be careful to see if there's a sign change. Remember, there's a sign change if both of the two numbers are congruent to 3 mod 4. However, you can obviously see from up here that 421, well, it's obviously congruent to 5 and therefore also congruent to 1 in mod 4. So I can actually go ahead and flip this one over with no sign change. And then the same thing on the second one because of the 421. Okay, so we flip those over with no other sign changes so far. All right, and so now I have, and I now should just reduce 421 in mod 7. And it turns out it's exactly equal to 1 in mod 7. So this is just the same as 1, the Legendre symbol of 1 in mod 7. And then we do the same thing in mod 13. Let's see. So if we divide 421 by 13 and take the remainder, I think, is it 5? I think it's 5. Yeah, it's just going to give me 5. So I'm just reducing in mod 13 right there. Anything that's a perfect square, we can just ignore. I'll get rid of the 1 over 7 one. And now I'm going to flip again, right? I'm going to flip this one again. Incidentally, guys, another way to do this kind of goes back to what Jamie was asking a few minutes ago. Another way to calculate this number is to just take all of the quadratic residues in mod 13 and see if 5 is there. So that wouldn't be so bad. I mean, obviously you don't want to do something like that with 421. That's way too big of a number. But 13 is reasonable. You just have to take 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. You take those numbers and you see if 5 is one of them, right? Okay, so that is certainly possible. Or, of course, the other thing you can do is just flip this back over again. Right, so the 13 over the 5, and that has no sign change because the 5 is congruent to 1 in mod 4. And now I just take 13 and reduce it to 3 in mod 5. Easy enough to do that. And we can see that 3 is not a quadratic residue in mod 5, right? 1 squared is not 3. 2 squared is not 3. So that means that 3 is a non-residue. So we're going to have -1 for that. And so the 2 minus 1s multiply, and we end up with +1 as our answer. The answer is always, of course, plus or minus 1, but we should always show our work, of course. Okay. Everybody okay so far? Making some pretty good sense? Okay. Well, only have one problem left, and it's probably good because I do need to try to wrap this up close to on time because I have my 250B students might be trying to ask me some questions starting at 9 o'clock here. So, but we have about 8 minutes left. So I think I'm going to put this last problem on the board. Just one more thing. Remember, guys, as we go away from these review sessions, I haven't been able to like practice everything. Obviously, I've tried to hit some highlights between Friday and today. You know, we did a lot on the recent material on Friday, and tonight we've been going back to some of the older things. But yeah, you need to still look at other things, like, because I have not written the final yet, and I don't know for sure, you know, there could be something I get excited about that's that wasn't something I directly spend a lot of emphasis on here, but I definitely feel like we're getting a lot of things done. One thing I think I forgot to say on Friday also, guys, is make sure you know the definitions of things, the basic definitions. What is a quadratic residue? What is a primitive root? What is the order of an element? What is a perfect number? You know, what is a prime for that matter? And then some of the really famous named results. The fundamental theorem of arithmetic. Obviously the Chinese remainder theorem, the Euclidean algorithm, the Fermat's little theorem, things like that. You should definitely be sure to get some flashcards. You probably already have some from before. But I might just ask you, I didn't do a lot of that on the second test. I wanted to do more, but I just didn't have enough questions, I guess, to do that. But I might just ask you to give me some of these basic definitions. And with those kind of things, I am pretty fussy. Like the definition has to be mathematically precise, for instance, or the statement of a theorem. You got to have all the assumptions in there. The conclusion has to be correct and everything else. So those should be easy points to get on the test, but I'm always surprised at how many people are just a little careless. It's not that they don't know it, I don't think. It's just that attention to detail is really important on those kinds of things. You know, some of these more complex problems, I can deal with a little bit of sloppiness, or you're trying to like figure it out as you go along. You don't really know how to do the problem. That's understandable that you'd have chicken scratch and stuff like that all over. But when it comes to just a crisp statement of a theorem or a definition or something like that, I do have a little higher standard there. So try your best to really think it through as you're writing it down on the test, because I really do think you guys know these things, and sometimes it just doesn't end up on the paper quite the way it needs to. Okay. Anyway, so I forgot to say that on Friday about sort of taking a look at just those basic number theory concepts that we've looked at, and go from there. Okay, let's do one more problem. I confess, guys, I'm sorry, I don't have any cryptography review problems. You guys just finished your term papers. I think a lot of you have that pretty fresh in your mind. It is possible I could ask about that as well, but I'm just not going to have time to really review it here. If you do have questions, of course, office hours are always an option. So here is the problem, number 11, I guess it would be. And it just says solve the system Okay, so the first equation is 10x to the 6th congruent to 3 in mod 13. And secondly, 16x is congruent to 26 in mod 50. Now, if I multiply 13 and 50 together, I will just point out here that you get 650. Now, that does not mean that we necessarily have only one unique answer in mod 650. And the reason for that is that some of these congruences may have more than one solution. In fact, does anybody see something I could do right away that would simplify this problem a little bit?
You can divide the second one by 2, right?
Exactly. There is a common factor of 2 in all of the expressions in the second congruence. So the very first thing I would do would be to just cut the second one in half. So 8x congruent to 13 mod 25. Okay, so already if I do that, now I'm looking at maybe getting, you know, solutions that are represented in mod 325 instead of 650. So 25 times 13 is 325. So you can see now that the second congruence actually will have a unique solution. This is if we just look at the second one for a moment, guys, this is simply a linear congruence. And you can get rid of this 8 very easily because 8 is relatively prime to 25. In fact, if you multiply this one through, can somebody just eyeball it? What could you multiply the second congruence by that would solve it for x for us? Can you see it in your head? Yeah, Byron, very good. See, if you just say 8 times 3, you get 24. In the world of mod 25, negative 24 is the same as 1. So if I just multiply by negative 3, I can actually simplify this as well. So negative 3, that would be negative 39. I'm going to change that to positive 11 in mod 25. Okay, so x is congruent to 11 in mod 25. We've got that much figured out. And that's just coming from the second congruence. Now, if I want to go back to the first congruence, obviously I can get rid of the 10 if I want to by finding an inverse. In fact, we could just take let's just do the same idea here, guys. Let's just multiply through by 4. Because 10 times 4 is 40. And in mod 13, 40 is the same as 1. So I multiply through by 4, and I'll write it over here. I get x to the 6th congruent to 4 times 3 is 12. I'm going to write that as negative. Well, I'll just write it as 12. It's fine. In mod 13. Doesn't matter. So let me add a little box to that as well. So I've got these 2 boxed congruences now. And so any suggestions how I'm going to proceed from here? To solve, the goal is to solve for x if that's possible.
I think by inspection, x's can be 2, right?
X can be 2. Yeah, you got that by inspection, didn't you? But of course, there could be more than one solution. And in fact, if you're telling me that 2 is a solution, you might have another one that you could tell me also is a solution.
Negative 2?
Right, because you're taking 6th power here. So 2 or negative 2 would definitely work. But according to Lagrange's theorem, I could potentially have as many as 6 different solutions. This is a 6th degree equation. So I could be missing some. Now, I might say something on the test, guys, like do not use a calculator. Or I might make my modulus big enough that you won't feel like just brute forcing. I mean, honestly, if you wanted to, you could just take all 13 integers, square all of them, and 6th power all of them, and see if you get 12. And you get all the solutions that way. And you're right, Ben, you'd come up with 2 and negative 2 as solutions. but there are potentially more than that. There could be as many as 6 solutions. Byron's got an idea in the, oh, that was a different thing he was talking about, but there could be other solutions as well. So I'm wondering, other than brute force, because I'm not real excited about brute force, especially when we've learned some stuff that could help us. What is another way that we could solve this, these 2 boxes for X?
Could you use indices?
Yeah, what I need to do, right, I would like to use the Chinese remainder theorem, ultimately. I have mod 25 and mod 13. They are relatively prime. If I can just get rid of the 6th power of X, then I'd be in good shape. So I would say the way to do that, and we've done this before, guys, when you're solving congruences with large powers on them, we can use indices. So let me write this down here. We're just going to take the index of both sides relative to some primitive root r, which I'm not sure what that is yet. So the index relative to r of x to the 6th, congruent to the index relative to r of 12. And this is always in mod phi of n. Phi of 13 is actually 12. And the reason that this is such a nice way to proceed is that you can use the logarithm properties that you know. So I can take this 6th power and write it down in front. Okay, so I'm just going to do that. So I pull the 6 down in front, and now I've got an equation that kind of looks like this. What are we really going to need to do, though, in order to get any further with this problem?
Find a primitive root of 13 and form that little table of indices.
Yeah, exactly, Tuan. We have to find a primitive root to start off with. Where do you suppose we're going to get a primitive root for 13 from?
From the table that you give us.
Yeah, from the table that I'm going to give you guys, right? If it's a prime number, it's going to be in that table. Or if my congruence happens to be in mod 27, I might have part A to be find a primitive root of 27. And then in part B, okay, solve my system of congruences, right? I can kind of paste together questions that way. I don't necessarily have to do that. I mean, I don't like to create lots of parts to problems that are depending on each other in case somebody makes a mistake on one part, it doesn't screw up the whole thing. But anyway, yeah, I mean, we do know how to find primitive roots. That's really the moral of my lesson here. So we just have to choose a primitive root. I believe that, if I remember correctly, that 2 is a primitive root here. Yeah, so we can choose any primitive root we'd like, but we could choose r equals 2. That would be a perfectly good choice for a primitive root. And then we just make out the table, okay? And I'm gonna ask you guys to review that on your own because I am a little bit over time and I'm gonna need to kind of quit a little bit early here. But essentially, you will ultimately end up getting, I'll let you guys check this using a table of indices, kind of view this as a little thing for you guys to practice. You guys can check that X itself, there are actually 6 choices here. 2, 5, 6, 7, 8, or 11. Those are the 6 choices. This is in mod 13. So using a table of indices and plugging everything into this little equation here, you can see that. Okay. Basically, what's going to happen, I'm just going to tell you what's going to happen right here, is that you're going to, the condition is going to be that the index in base 2 of X has to be odd. You'll discover that if you do the work correctly, you'll discover that it has to be odd in mod 11, which in mod 12, which means it has to be 1, 3, 5, 7, 9, or 11. There are 6 different possible X's that will have, you know, an odd index. And these are them right here. You might notice that the last 3 values are just the negatives of the first 3 values, which makes sense because you're taking 6th powers. So anytime you have a positive solution for X, the negative of that positive value is also going to be another solution. This means that you're going to have 6 CRTs. 6 Chinese remainder theorems, because you have to take each one of these and combine it as an equation with this one over here. And so you're doing this little system 6 times. Certainly not necessary really to do that. In fact, I don't even have all the answers written out of what they should be. But you guys can obviously hopefully come up with the 6 answers using the Chinese remainder theorem, and then check your answer. Take your answers, raise them to the 6th power, multiply by 10, and make sure it's congruent to 3 in mod 13. Same thing with the second congruence. You can check that it satisfies that as well. So there's some details here I didn't have time to really fully finish, but I hope I've given you the roadmap anyway, of how you would get there.
So if we would do this whole problem, the first time we do it, we can use a CRT, right? But the second time we do it, we can't use it because mod 13 would not be relatively prime with the first round that we did, right? Does that make sense? Or can we knock this out?
No, the moduli are 25 and 13. These 6 choices together with this one here, you can use the CRT 6 times. So each time you're using it, it's a system of just 2 equations. We're not trying to combine them all together, Ben. It's just this equation here. It's just this one right here together with each one of these one at a time.
Okay, I see it now.
Did you catch that? My thing said the internet was unstable for a minute. Did I?
Yeah, I was able to put it together.
Okay, yeah, sorry. So let me just repeat that in case anybody missed it. My internet has been kind of in and out today with the weather. Right? We're not trying to like do a system of like 6 equations all at once right now. It's just this equation and one of these 6. So you have a system of only 2 equations. It's just that when you solve that system, then you start over with this equation and a different one of these 6. So you're not like lumping a system together where you keep adding congruences to what you had before. No, you're starting fresh with a new system of a mod 25 and a mod 13. And every one of those new systems can be done with the CRT. Right. Okay, well, I think this is pretty good. We basically got through all of these notes, which is fantastic. I pretty much did all the problems I was planning to do and even a couple of extra ones. I don't know how you feel. Hopefully you don't feel worse. Hopefully you feel better. Like, okay, you know, this seems manageable. I've kind of seen all this stuff before. But yeah, I wanted to get together with you guys and help you see some examples of the kinds of problems that I might ask you. The sample test is going to be another great resource to see some more problems that'll be, you know, kind of along the lines of what I'm thinking as I'm writing this test. You know, you've got a lot of practice problems everywhere, probably too many to do. Try not to let yourself get so stressed out. It's like, oh my God, there's like 500 different problems I could try to work right now. You don't have to do all of that, right? I like there to be tons of resources for everybody, but I understand it could look overwhelming. You have to just pick and choose what things you're going to focus on, which should be the proofs, obviously, and then whatever you're maybe not feeling as strong about. And the purpose of the review is really just to sort of remind you about some topics so that you don't just completely overlook something and then get to it on the test and have no idea. It's like, oh my God, I haven't looked at this since February or something. So I wanted to make sure that, I tried to poke at as many different things from the last 15 weeks as I could. I don't promise that I didn't miss something, but I'm pretty sure we were pretty thorough. Like, I feel pretty good that between Friday and today, we talked about a lot of good stuff. So I'll let you guys take all of that and run with it. Work on the studying as best you can on your own, looking at those resources, and then stop by my office hours. You can come hang out any night, tonight, tomorrow, Tuesday, Wednesday, even before the test. I should be around. So I'll be around quite a bit, and I've been trying to hang with you guys all semester long. I'm not going to disappear on you now. We're going to get through these next 3 or 4 days and get to the other side of it. Okay. Thank you for coming. Appreciate it. Does anybody have any last questions before we go?
Yeah, Dr. Annan. So come at 5, right? Don't come earlier than 5 on test day.
Well, you can come in a few minutes early. That's fine. I mean, I will, I'm sure, be there a little early. Since I'm not going to be cutting you guys off like right at 7, I'm not as quite so worried about having people get their technology going and get their setup ready and the exam printed and everything. But yeah, I'll be there a few minutes early.
Okay, thank you.
Yeah, you can just come on into Zoom and then I'll let you in as soon as I'm ready for you. Any other questions? All right, I'm gonna zoom on over, no pun intended, zoom on over to my other Zoom room where my office hours are. So I'll be there for the next 2 hours and 45 minutes anyway for tonight. So have a great rest of your evening, everybody, and good luck with all of your finals, this one included, but I know you've got other things going on. It's a busy time. Take good care of yourselves, get some rest along the way, and let me know if anything I can do to help, okay? Have a great night. Thanks for being here, and I look forward to seeing you guys again real soon. All right.
Thank
take care.
you.
You're welcome, everyone.